If you're given the values, you need to do calculations. So how do I do the calculations when I have my sig figs? Adding and subtracting rules, you're going to round to the smallest common decimal place. Let's take a look at an example of that. So if I have 3.427 plus 12.3 plus 0.85. Now if I plug all those numbers into my calculator, I get 16.577. But if I take a look at my digits to the smallest common decimal place, well, this one goes to 10 hundred thousandths. This one only goes to tenths. This goes to hundredths. So if I go to thousandths, I have to have hundredths and tenths. But that's the only one that goes to thousandths right here. So I can't go to that decimal place. I've got two of them, this one and this one, that go to hundred, but the middle one does not, so I can't stop there. All three of them, however, have a digit in the tenths place, so that is going to be my smallest common decimal place, and so I have to round my answer to that number of sig figs. So I'm going to have 16.6 because I'm rounding 0.577 to 0.6. So when I'm adding or subtracting, that's how I deal with sig figs. When I multiply or divide, I want my final answer to have the same number of sig figs as the value that has the fewest sig figs. So let's take these same three numbers. So I have 3.427 times 12.3 times 0.85. If I multiply them all together on my calculator, I get 35.289285. Now I'm looking for something that has the fewest sig figs. So that means I have to go back and count how many sig figs each of my values has. This one has 4, this one has 3, this one has 2, because the 0 is a placeholder there, it's not significant. So what that means is I have to round my answer.
Let's do a quick
to
check
only
of how
two
to deal
sig
with
figs.
zeros.
So I round all that and I end up with plain old 35. Now when I have both types of operations in one set of calculations, I work from the inside out. So whatever's inside my parenthesis, I do those operations first, get that number to the correct sig figs, and then move on to the next type of operation. So if I have a number that has zeros in it, how do I figure out if the 0 is significant? Let's take a look at a couple of examples. So I have 402, I have 30.07. One quick and easy way to remember zeros is it's either between two non-zeros or it has to be right twice. We'll take a look at both of these. So between two non-zeros, that takes care of this one. So 4 and 2 are significant, so the 0 is also significant, so I have 3 sig figs in the first number. Here I have 2 zeros between two non-zeros. The zeros, therefore, are also significant, so I have 4 sig figs here. Here I have a 0 that's not between non-zeros. It's to the left of the decimal, not to the right, so therefore it's not significant. It's not to the right of any non-zeros, so it is not significant. I only have 2 sig figs here. So let's go back and clarify. Right twice, right of the decimal to the right of a non-zero. Let's take a look at our example for 400. These 2 zeros are both to the right of 4, but there's no decimal. So they are in fact just placeholders, and what I could do is write this in scientific notation, which is 4 times 10 to the 2. This tells me there's only one sig fig, and that's the 4. If I take a look at the next one, the only thing different between this one and the one above it is that decimal. Again, the zeros are to the right of a non-zero, but the decimal there is an indicator that I can measure accurately to the ones place. If I can measure accurately to the ones place, that means that this 0 is significant. So this gives me 3 sig figs, and if I were to write it in scientific notation, it would be 4.00 times 10 to the 2. So a decimal can make a lot of difference in numbers. Okay, we're going to talk a little bit about uncertainty, primarily in terms of making measurements. We're not going to include uncertainty in our calculations. The uncertainty simply is looking at the sig figs and what decimal place is accurately graduated and what decimal place do I have to estimate. So the plus minus value is a measure of the estimated digit. So if I go back to my beaker, we said the beaker was 65 milliliters. And we'll say it's plus or minus. We can probably can't estimate 1 milliliter since our divisions are tens. I might be able to estimate 3, 4, or 5 milliliters. If I think I'm really good, I can say it's plus or minus 3 milliliters. I could say it's plus or minus 5 milliliters. Plus or minus 1, that's pushing it. Probably can't do that. On this one, I have 19.17. We said 2 before. We'll call it milliliters. This is going to be plus or minus 0.00 because that third decimal place is where we're making our estimate. We can say plus or minus 0.001, 0.002, whichever one you feel comfortable with. Again, we're not going to be including these plus or minus numbers in our calculations, but it's something you need to be aware of when you are making measurements so that you know how you're estimating and what decimal place is uncertain. The uncertainty simply means that digit you're estimating is the one you're uncertain about. Another thing we're going to talk about when we're making measurements is accuracy versus precision. If we take a look at the left-hand diagram, we have our bullseye, or the goal we are aiming for, right here in the middle, and we've got a shot here, one here, and one here. Not very accurate, not very precise. Accuracy means how close can you get to the actual value. If we take a look at our middle chart again, here's our target, and we have 4 tries again. They're all really close together, but they're not anywhere near the target. Now we're being precise, and precision we're going to describe as being repeatable, consistent, values close together. Precision is good, accuracy is good. Ideally, you want both. So in our last example here, again, our target's in the middle, and what we can see is all 4 shots are close to each other, so they are precise. They are also close to the target, so they are accurate. When we calculate a percent error, that is generally a way to determine how accurate we were in our measurements. When we do multiple trials and make multiple measurements of a particular reaction, temperature, etc., then we're looking at precision. Actually, most of the labs that we're going to be dealing with, we aren't going to be doing many repeatable trials, so we're not going to actually have the opportunity to work much with precision. Percent error, just a reminder, you have your observed value minus your actual value. Your observed can be your experimental, and you divide it all by the actual value. We're going for absolute value, and then ultimately you want to multiply it by 100%, because this will give you a decimal, some number, usually, hopefully, less than 1, but close to it, and then you want to get into percents by multiplying it by that 100%.